In this video, we'll take a few minutes to explore the popular G5RV multiband antenna. Louis Varney, G5RV, developed his multiband antenna in 1946. During World War II, he served in the Royal Corps of Signals in an interception and direction-finding unit. After retiring from the military, he moved to a house in Stony Stratford that had a garden barely 100 feet long. His desire for a multi-band antenna resulted in the design now universally known as the G5RV multi-band HF dipole. Varney never made a profit from his antenna and passed away in the year 2000 at the age of 89. So let's take a look at the classic G5RV antenna. Interestingly, the G5RV is not designed to be resonant at the lowest frequency of use. In fact, it was designed for 20 meters, but for a length of 3 half wavelengths. This means that the feed is at a point where the current is at a maximum, as shown in this diagram. The resonant impedance at the feed point should be approximately 90 ohms. Next, Varney planned for a half wavelength of open wire ladder line with a characteristic impedance in the 300 ohm range to serve as a one-to-one transmission line transformer to a point that would transition to a coaxial cable with a characteristic impedance of perhaps 75 ohms. Thus, at 20 meters, the impedance at the transition to coax should still be resistive at approximately 90 ohms, yielding a standing wave ratio of about 1.8 with 50 ohm coax. The 3 current lobes act as a collinear array that produces a more complicated radiation pattern than a standard dipole, and we shall see examples of these patterns later in the video. Varney also reasoned that at other frequencies, the upper part of the ladder line would act with the flat top to behave as a folded antenna. The lower part of the ladder line transmission line transformer would be less than 1/2 wavelength, thereby producing unwanted reactance at the transition to coaxial cable. When Varney conceived this antenna in the 1940s, most transmitters used impedance matching output couplers, such as pi networks, that could easily handle these unwanted reactances. With today's solid-state transmitters designed for 50 ohm loads, an antenna tuner is required to take advantage of the G5RV multiband capabilities. One final point: today's antenna tuners have a finite range of impedances they can match to 50 ohms. If your tuner fails to achieve a desirable match at a particular frequency, you can try changing the length of coax between the tuner and the ladder line section of the G5RV. Later in this video, we'll model one specific tuner to see how the G5RV works over several amateur bands. So what's a classic G5RV? Varney used the formula on the left, where n is the number of half wavelengths for the antenna. Note this is not the usual formula for a dipole antenna that you see in the handbooks today, but this is what he used with n equals 3 for the 3 half wavelengths. For his 14.15 megahertz design point, he calculated a length of 102.57 feet, but rounded this to an even 102 feet, which is the number that is almost always quoted for a G5RV antenna. Varney mentions 2 possibilities for the transformer section. The first is 34 feet of open wire feeder made from number 14 wire, which is presumably 534 ohm ladder line. And the second suggestion is 28 feet of 300 ohm ribbon line. A more modern possibility would be 30.6 feet of 450 ohm window line like Wireman number 554. Varney was far less specific about the feeder line, but does mention 50 or 80 ohm coaxial cable with lengths up to 70 feet, 75 ohm twin lead, or 84 feet of open wire transmission line. Recent publications have suggested various lengths of different coaxial cables shown in the lower left. So let's take a look at a specific tweak to the classic G5RV that we'll evaluate using computer antenna modeling. Instead of the standard 102 feet, we'll use a slightly longer 106 feet. The transformer section is based on Wireman 554 450 ohm window line. Interestingly, the ARRL software TLW, or Transmission Line for Windows version 3.24 by Dean Straw N6BV, gives the actual characteristic impedance of the Wireman 554 as 402.7 minus J 0.85 ohms, which we'll say is 403 ohms. If we want to see the currents in the transformer section, it's easier to model it as a two-wire ladder line. So using the formula shown here for the characteristic impedance with an air dielectric, we'll consider two number 14 wires with a diameter of 1.62 millimeters spaced at 23.46 millimeters apart. We'll say this ladder line is 31.9 feet long, or 9.72 meters. The antenna will be 35.3 feet, or 10.76 meters above the ground, and we'll choose 49 feet of LMR 400 50 ohm coaxial cable. Here's a quick scan of the standing wave ratio at the input to the coaxial cable section using the EZNEC or EZNEC antenna modeling program. Several frequencies toward the lower end of the popular high-frequency bands are shown by the red dots. Some of these standing wave ratios can look scary to those of us striving for a standing wave ratio of 1:1, but to get a little ahead of the story, I can tell you that all these frequencies can be matched with a modern, commercially available antenna tuner. However, it's fair to say that the G5RV is a compromise designed to achieve multiband operation. But only the performance at 17 and 10 meters may deserve the most scrutiny. Okay, it's time to dive into more of the modeling results. We'll be using an antenna modeler called MMANA GAL. The basic version is available free of charge at this website, where more information about the program and the authors is available. The antenna model consists of 5 wires, 2 across the top from the end insulators to the center insulator, and the 2 wires comprising the ladder line described earlier running vertically from the center insulator to approximately 1 meter above the ground. The final wire connects the 2 lower ends of the ladder line with a source positioned in the middle. This is where the coaxial connector would be connected, but the coaxial cable is not included in the model. We'll start by looking at the performance at 14.12 MHz in the 20 meter band, since this is the basic design point for the G5RV. Here are the electrical results. The impedance at the bottom of the transformer section is 136.7 plus J 0.12 ohms, which is very close to a pure resistance of 137 ohms. This is a standing wave ratio of 2.73, assuming 50 ohms. The fact that the impedance at this point is resistive, with very little reactance, validates the basic design point at 20 meters. Here are the current amplitudes at 14.12 MHz, and we can see the 3/2 wavelength appearance along the flat top, and we can also see the current along the vertical ladder line. Now for the antenna patterns on 20 meters. The azimuthal pattern is on the left, and the x-axis, which is broadside to the antenna, runs vertically. You can see that the strongest radiation is approximately plus or minus 45 degrees from the y-axis, which is where the wires of the antenna lie. The elevation plot is along the x-axis, or broadside to the antenna, and the strongest signal is just below 30 degrees above the horizon. Let's continue to follow the electrical path back towards the transceiver. The 49 feet through the LMR 400 coax transforms the impedance to 23.94 plus J 21.37 ohms at the input to the antenna tuner. More about the tuner in a minute. The coax also adds a total loss of 0.36 dB, which includes a 0.14 dB penalty due to the standing waves that are present in the coax. Finally, to see if we can transform the impedance at the output of the coax to 50 ohms, we'll look at the AT Auto tuner that uses a differential capacitor and a variable inductor. This is similar to the MFJ 986 antenna tuner. The differential capacitor has two mechanically linked sections, such that as the capacitor is adjusted, one side decreases in value as the other side increases. The capacitors in this case have a minimum value of 14 picofarads and a maximum value of 340 picofarads. The inductor ranges in value from 0.1 microhenries to 26 microhenries. We can see how the matching works on a Smith chart. First, we plot the impedance at the input of the tuner of 23.94 plus J 21.37 on the Smith chart. Next, we add a series capacitance of 162 picofarads for C2 and move along a curve of constant resistance. Next, we add the parallel inductor of 0.425 microhenries and move along a curve of constant conductance. Now we add the final series capacitance C1 of 192 picofarads and move along a curve of constant resistance to the prime center of the Smith chart, which represents 50 ohms and a standing wave ratio of 1:1. So now we have the complete picture for 20 meters. We were able to present a 50 ohm impedance to our transceiver and have only lost 0.36 dB or 8% in power. Let's move away from the design point on 20 meters and look at the other bands. Here's the current amplitude at 3.7 megahertz along the flat top. It looks close to a half-wave antenna, with still a fairly large current in the transformer section. The azimuthal far-field plot looks more like a dipole, with the maximum propagation broadside to the antenna along the x-axis. The elevation plot on the right side shows most of the energy going upward at right angles to the ground. The standing wave ratio at the bottom of the transformer section is 4.8 with an impedance of 16.90 plus J 35.67 ohms, which is a magnitude of 39.5 at an angle of 64.6 degrees. The LMR 400 coax transforms this impedance to 48.53 minus J 81.43 ohms, or a magnitude of 94.8 ohms at an angle of minus 59.2 degrees. The total loss in the coax is 0.11 dB, with no penalty for the standing wave ratio, and represents a power loss of only 3%. Finally, the AT Auto antenna tuner has no trouble transforming the impedance to 50 ohms, so everything looks pretty good here at 80 meters. Moving along to the 40-meter band, let's take a look at the antenna current magnitudes at 7.15 megahertz. It looks like the wire is not quite a full wavelength long, and a current minimum has appeared in the transformer section. The azimuthal pattern still shows the strongest direction is broadside to the antenna along the x-axis, and the elevation plot indicates strong radiation perpendicular to the ground. Let's quickly review the electrical parameters. The standing wave ratio at the bottom of the transformer section is 10.5, and the impedance magnitude is 159.3 ohms with an angle of minus 70.9 degrees, which indicates a fairly strong capacitive component. The 49 feet of LMR 400 coax transforms this to a standing wave ratio of 8.73 with an impedance magnitude of 200.9 ohms and an angle of 60.8 degrees. The total loss in the coax is 0.9 dB with a 0.75 dB penalty for the standing wave ratio in the line. This represents a signal loss of approximately 19%. Once again, the AT Auto antenna tuner has no difficulty matching the coax to 50 ohms. So if we're willing to tolerate the signal loss, the performance seems quite reasonable. Moving along to 17 meters, things get a little more interesting. Here is the plot of current magnitude at 18.12 megahertz. The wire is almost 2 wavelengths long, and the feed point is very close to a current minimum. There is also a current minimum near the bottom of the transformer section. The azimuthal far field plot shows an extreme null broadside to the antenna along the x-axis. There is also a less extreme null along the direction of the antenna, which is aligned with the y-axis. The pattern has a maxima at approximately 55 degrees from the y-axis. The elevation plot along the x-axis is almost non-existent and further illustrates the extreme null along the x-axis. It's interesting to look at a 3D plot of the far field antenna pattern produced with the EZ-NEC modeler. You can see the sharp, deep null broadside to the antenna. The standing wave ratio at the bottom of the transformer section is a whopping 61.5 with an impedance of 625.9 ohms at an angle of minus 86.9 degrees, which is strongly capacitive. The LMR 400 coax transforms this to 99.1 ohms at an angle of minus 83.7 degrees and a standing wave ratio of 21.7. These high standing wave ratios come at a price, though, and the total loss in the coax is 4.36 decibels with a penalty of 4.11 decibels. This represents a loss in power of 63%. Once again, the AT Auto tuner is capable of producing a 50 ohm impedance for our transceiver. The significant difference in the 17 meter case is the loss of power in the 49 feet of LMR 400 coax. Let's look quickly at 15 meters. Here's the plot of current magnitudes, and we can see more current maxima appearing along both the flat top wire and the transformer section. This leads to more complex far field plots as shown here. The maximum radiation is approximately plus and minus 30 degrees away from the x-axis. The electrical performance at 15 meters shows more moderate standing wave ratios and impedances, with the total power loss in the LMR 400 coax at 0.49 dB, or about 11%. Once again, the tuner has no difficulty creating a 50 ohm load for the transceiver. Here is the plot of current magnitudes at 12 meters. The antenna is slightly more than 5 half wavelengths long, and the feed point is near a current maximum. The azimuthal far field plot has substantial lobes approximately plus and minus 36 degrees from the y-axis. The electrical performance is one of the best we've seen, with the standing wave ratio equal to 1.81 at the bottom of the transformer section, with the impedance at 86.9 ohms at a minus 12 degrees. The standing wave ratio at the input to the tuner is 1.73 with an impedance of 86.3 ohms at 4.2 degrees, which is almost pure resistance. The loss in the LMR 400 coaxial cable has dropped to 0.36 dB, or a power reduction of only 8%. The last band to look at is 10 meters at a frequency of 28.3 megahertz. The wire is just over 3 wavelengths long, and the transformer section is about 1 wavelength long. The azimuthal far-field plot has 6 lobes, with the strongest being about plus or minus 46 degrees from the y-axis containing the long wire. The MMANA two-dimensional azimuthal plot is deceptively simple, however, and here is another 3-dimensional plot from the EZNEC program. Here you can see there is a lot going on above the XY plane. It is certainly a complex far-field pattern. The standing wave ratio is again rather large, and the impedance at the bottom end of the transformer section is 1039.7 ohms at an angle of 69.6 degrees. The standing wave ratio at the tuner input is much lower, with a value of only 18.5, primarily because of the loss in the 49 feet of the LMR 400 coax. In fact, the total loss in the coax is 4.96 decibels, which represents a power loss of 68%. The AT Auto Tuner is capable of providing a 50 ohm impedance to the transceiver one more time. There's no question that the G5RV multi-band dipole is a popular antenna. Almost all amateur radio suppliers have a version for sale. You constantly hear users mention it on the air, and it is common on field day sites. The idea of one antenna to cover operation on multiple HF bands is certainly attractive, it is low cost, and it's not difficult to build. But the user should understand up front that it is a compromise antenna in the sense that better antennas are possible when tailored for a specific band or frequency. The G5RV works well on some bands, but not on all HF bands. The actual performance will vary with the final dimensions and choice of transmission lines, but for the specific case we have examined, we can conclude that the G5RV has acceptable losses using a modern antenna tuner on the 80, 40, 20, 15, and 12 meter amateur bands. It should be pointed out that we have ignored losses in both the ladder line transformer section and in the antenna tuner. Nevertheless, the G5RV deserves its place in the arsenal of low-cost antennas available to today's amateur radio operator.